Today we're going to look at how to write and name ionic compounds. First of all, what we need to remember is that ionic compounds always involve a metal and a non-metal. So what you need to have out is your periodic table of elements. Both the front side and the back side will be very critical to you in the minutes ahead. Now, the first thing I want you to do is make sure that you have clearly outlined the separation line between the metals and the non-metals. So if you haven't done that so far on your periodic table, do that now. Remember that metals tend to lose electrons and become positive ions, while non-metals tend to gain electrons and become negative ions, or anions. So let's just take a few moments to make sure that we have all the information on our periodic tables that we need in order to deal with ionic compounds. First of all, make sure that you realize that this first column over here on the left, these are the +1 ions. Hydrogen, remember, is in a section by itself. It's not a metal, but like the rest of the alkali metals, hydrogen will, when it loses electron, will only lose one electron. Right next to it, beryllium and its family of alkaline metals will lose 2 electrons. Over here, aluminum, the +3, its neighbor gallium, +3, indium, +3, thallium, +3. Come over here to number 50, tin. Tin begins our sections of metals that can lose multiple types of electrons. Sometimes it loses 1, sometimes it loses 2, sometimes it loses 3. They cannot be relied on. So you really need to know ahead of time. And here in a few minutes we'll know how to communicate to somebody whether you want them to think of tin as being +2 or tin as being +4. Lead also can be either 2 or 4. Now let's move over here to the transition metals, and let's focus on our friend iron, number 26. Iron can be either number +2 or +3. Nickel, +2, +4. Copper can be either +1 or +2, but silver below it is always +1. Zinc and cadmium are always +2. Mercury is the oddest duck on the periodic table. I want you to, I think you have some room over here on your periodic table, a little asterisk by Mercury, because Mercury is a very strange little animal. Mercury 1 actually does not exist by itself. Mercury 1 will always have a twin attached to it. So if it's Mercury 1, you will always see it as Hg2 +2. The 2 meaning that there are 2 mercuries next to each other, and the +2 meaning that together both of them are +1, therefore they have a charge of +2. Now, just to confuse you really well, you must realize that Mercury 2 is normal. It is what we would think Mercury 2 would look like. It is 1 mercury with a +2 charge. So, when you see Mercury 1, you need to think, hey, there are 2 Mercury 1s tied together. When you see Mercury 2, then there's not 2 mercuries. There's only 1 mercury with a +2 charge. They both have +2 charges. It's okay to have this down on your periodic table as a reminder. And that's pretty much it. All of these guys here, all these transition metals, all of them will have multiple charges Most of the time, we will not ask you for the name of these guys. Um, we may give you these guys along with their Roman numeral in order to denote their charge. Um, in which case you will know its charge based on the Roman numeral. Alright, so let's get started. Sodium oxide. Notice, first of all, that sodium does not have a charge. What that means is that sodium has the charge that it normally has, which, since sodium is in the first column, that means it has a +1 charge. Oh, wait a second. We forgot about the negative ions. Alright, so let's go back here to the negative side, and noble gases, of course, will have no charge. They do not tend to lose or gain any electrons. Fluorine, chlorine, bromine, iodine, not aspartame. Aspartame is a metalloid. Uh, these guys tend to gain 1 electrons, therefore it is a -1 charge. Oxygen tends to gain 2, and nitrogen, phosphorus, arsenic tend to gain 3. Carbon and silicon do not tend to form ionic compounds, so we're going to leave them along with the metalloid boron. Okay, now I think we're ready. Let me change my pen back to white for you to see better. Alright, so sodium has a +1 charge. It's in the first column. Check it out for yourself. Oxide ends in IDE, which means it's more than likely a nonmetal. Now, some polyatomic ions do end in IDE. The closest one to this one is hydroxide. Hydroxide is OH-1, but we're not talking about hydroxide here. We are talking about oxygen. So put down oxygen, -2. Remember from our lab, now we need to make sure that both sides equal out. We've got the positive side, negative side. Obviously, we have too many negatives, so we're going to need to add another sodium in order to balance it out. So, the final result is sodium, and there are 2 of them, oxide, Na2O. Remember to pretty much, since the +1 and the 2 +1s cancel out with the -2, they are canceled. We don't need them anymore. And this is our answer. Magnesium chloride. Find magnesium on the periodic table. It's close to sodium. It is magnesium, and it has a +2 charge. Chloride ends in IDE, more than likely an element, and there is an element that is close to chloride. It's chlorine, and chlorine has a -1 charge. Once again, we've got the positive, negative side. Notice the positive side has a +2, the negative side has a -1. We need another chloride in order to completely cancel that out. So, Mg, and we have 2 Cl. MgCl2 is our answer. Alright, let's try this one. Barium sulfide. Barium, find it on the periodic table. Ba is charged +2. This is the same column as magnesium. Sulfide ends in IDE. More than likely it's an element, and sure enough, there is a sulfur. It has a -2 charge. Plus, minus. Notice that they cancel out right off the bat. So the answer is BAS. Copper 2 chloride. Now we're encountering the first of our what we call type 2 ions, ions that have multiple charges. If you look on the periodic table, you'll find that copper can be either +1 or +2. Gee, I wonder which one it is. The Roman numeral tells you which one it is. So, copper +2, chloride, is -1. We have too many positives. We need an extra negative. So those cross out. CuCl2. Iron 3 oxide. Once again, it's a type 2. You see it by the Roman numeral. If you look it up on the periodic table, you'll find that iron has that old Latin abbreviation for ferrum, or ferric. In this case, it would be ferric because it's the higher of the two charges. Ferric. If it's the lower of the two charges, it has an OUS ending. And that was an old way of denoting whether it had the higher or lower charge. So you had to automatically memorize whether it was 3 or 2 or 1 or 2 or 2 or 4. And the ick or the us would let you know which one it was. So an old way of saying this one would be ferric oxide. You might see that on the labels of some old bottles of reagents. Alright, so here we go. Iron plus 3. Oxygen is -2. This one's not going to work very easily, but you've already done some of these, so you know how it's going to work. We have too many positives, not enough negatives, so it would be really nice if we could add just one oxygen with a -1 charge, but you know that's not the way it works. If you need another oxygen, you have to have a -2 charge. So now, as you can see, we have a -4 and a +3. We don't have enough positives, so we add another +3. Now we have a +6 and a -2. That still doesn't work, so we're going to have to add our final ion, so that now we have -6 and +6. So they all cancel out. So Fe, there's 2 of them, O3. Mercury 1. Let's deal with Mercury because Mercury is a funny little guy. Mercury 1, by the way, what would we have called it back in the old days? Since Mercury comes in 2 forms, 1 and 2, number 1 would have been called Mercurus, and number 2 would have been called Mercuric. This time it's not using the old Latin word name for it. Alright, so Mercury 1 is that funny little guy where it's 2 Mercury 1s stuck together. So it's kind of like this. Mercury, Mercury, +1, +1. We simplify it just by writing it this way. Iodide, ID ending, probably an element, and it is. Iodine, -1. So we have too many positives, we need another -1. As you can imagine, you don't have to write all these iodines. After a while, you can see this in your head, and you can just go on and do it. So Mercury 1 iodide, it's like that. Mercury 2 iodide, or mercuric iodide, it's just plain old mercury with a +2 charge. Alright, it's -1, so it would be HgI2 because we would need 2 mercuries to offset. Now compare that to Mercury 1 iodide, and that would be Hg2I2. So it's kind of funny, but it is consistent that if you see a Mercury 1, you better have 2 mercuries. If you see a Mercury 2, then you will only have 1 mercury. I know, strange, contradictory, but it is what it is. Alright, here we go. These are perhaps the hardest ones of these to do because now we're dealing with polyatomic ions. Remember, polyatomic ions are groups of atoms that are covalently bonded. They're sharing electrons, but together they have an overall charge. So here is perhaps the most controversial of them all. mercury, that led to hydroxide, the hydroxide polyatomic ion. So, lead is a type 2. It can be either 2 or 4. In this case, it would be +2. We would actually use the old Latin name for this. It would be plumbus. It would be lead +2. Plumbic would be lead +4. Okay, so we have plumbus, lead 2, and hydroxide is not an element. I know it ends in IDE, but it is not an element. If you look on the back of the periodic table, you're going to find it there in your list of polyatomic ions. It is -1. OH, -1. Alright, so what you need to remember is to treat it as if it's one entity. So it's not H minus 1. It's not O minus 1. It is OH minus 1. So we have too many positives, not enough negatives, so we need another OH minus 1 in order to offset that. Now comes the tricky part. Lead, OH. Now we need to somehow denote that we have two OHs without confusing the person that's reading what we're trying to write down. If we were to place a 2 here, then it would look like there was one lead, one oxygen, and 2 hydrogen. Now we may have wanted to communicate, no, that's not the case, but it doesn't matter. That's the way it looks. So the rule is that when we have multiple members of a polyatomic ion, we use parentheses in order to avoid any confusion. So the parentheses is telling us that there are 2 of what's inside the parentheses. So the final answer here is PbOH2. PbOH2. No parentheses, it's wrong, because it could lead to confusion. So whenever you have more than one polyatomic ion, you need parentheses. Alright, let's try some more. Sodium +1. Notice that this ends in ATE. That is a huge indicator that you are dealing with a polyatomic ion. So look on the back of the periodic table. Is it there? Yes, it's there. Now don't confuse it with dichromate. Chromate is CrO4 -2. Dichromate is Cr2O7. It doesn't mean that there are 2 dichromates. It is a different polyatomic ion. Dichromate is Cr2O7. Okay, so here we have not enough positives. So it's going to be Na2CrO4. Okay, do we need parentheses? No, we don't need parentheses because we only have one of these things. If we were to use parentheses and put a 1 here, that would be redundant. We already understand that if we just have the formula there, there's at least one of them here. You don't need parentheses all the time. You only need parentheses when you have more than one of them. Now, some people are going to want to write it like this: CrO4. And that would be wrong, because the 4 is part of O. It doesn't mean that you have 4 of these things. It means that you have a Cr bonded to 4 oxygens. You don't have 4 Cros. You have CrO4. So it's Na2CrO4, no parentheses needed. How about this one? Tin 4 nitrate. Sn is +4. By the way, we would call it stannic because it has the higher of the 2 charges, and stannum is the Latin name for tin. Stannous would be +2. Okay, so stannic nitrate. So SN plus 4, nitrate ends in ATE, so NO3 negative 1. Now, 4 positives, 1 negative. You don't have to write these things down. You know what it's going to look like. SN, NO3, parentheses, 4. This one, it becomes a little more obvious why you need parentheses. Because if you did not use a parentheses, what would that look like? SNO3, 4. Well, you would say, well, no, obviously, it can't be 34. It would obviously be 4 NO3s. Okay, yeah, I understand. But you cannot leave that up to the interpretation. Put a parenthesis so that the person who's reading your formula understands that you have 4 of what's inside the parentheses. Ammonium phosphate. Remember, with all of these, you could stop the video, try it on by yourself, and then check your work with when you turn on the video again. All right, ammonium. Now you can look high and low for ammonium on the periodic table. You're not going to find it because there is one positive polyatomic ion, and its name is, you guessed it, ammonium. Ammonium. Phosphate ends in ATE. It's a polyatomic ion. It is PO4 negative 3. PO4 negative 3. Okay, so we have a positive 1, negative 3. As you can imagine, we're going to need 3 of these monstrosities. So, 3 PO4. I can hear you. Yep, right here. This is confusing. This looks like it's NH43 again. So how about if we do this? Parentheses to signify that we have 3 ammoniums bonded to a phosphate. Ionic, of course. All right. I have pretty much given you all the different possibilities that you might find when you're doing ionic compounds. Let's go on to trying to learn how to name these guys. All right, here we go. Sodium. Look it up on the periodic table. Does it have 1 charge or 2 charges? Just 1. It's always plus 1. So, easy peasy. Sodium, no Roman numeral necessary because it's obvious. Whoever you're communicating with has a periodic table as well, and they can look and see that indeed it is plus 1. No Roman numeral needed. Change sulfur to an IDE ending, so it becomes sulfide. The metallic name is never changed. The non-metallic name is changed to IDE. If you're dealing with a polyatomic ion, you don't change the name at all. Alright, what if you look up copper, and copper can be either plus 1 or plus 2. Now we've got a problem. First of all, at least we can get most of the name correct. Copper, once again, sulfide. Copper sulfide. The problem is that if you were to tell somebody, hey, what is the formula for copper sulfide? They would be in a quandary because they would have a 50-50 shot. They would look on the periodic table and see that it could either be 1 or 2, and they don't really know whether it's 1 or 2, so they would have to take a guess. So, what we're going to have to do is work backwards, do some detective work. Split the molecule in half, negative side, positive side. So which one is this? Well, we have 1 sulfur, correct? There's just 1 here. Just 1 sulfur, and sulfur we know has a negative 2 charge. So the sulfur side gives us a total of a negative 2 charge. You know that if this is a correct formula, then the positive side must offset that. These numbers must always be the same. One positive, one negative. Now, here is the question. What must be the charge on copper if 2 coppers times that number gives you positive 2? Well, obviously it's positive 1. 2 times what is positive 2? 2 times plus 1 is positive 2. So it is copper 1 sulfate. How about this one? Okay, so aluminum is always plus 3, so no worries. Aluminum. Here is a polyatomic ion. You never ever change polyatomic ions' names. It is sulfate. It remains sulfate. Aluminum sulfate. From this name, I can get this easily. Let me show you. Aluminum plus 3. Sulfate is SO4 negative 2. So you need, well, that's too many negatives. Need one of these. No, that's too many positives. Aha. That makes it just right. So 2 aluminums and 3, that doesn't look right. Same thing. How about this one? We got our mercury little beastie here. Do you remember? If you see 2 mercuries, it must be, yes, mercury 1. Non-metal gets named, this is bromine. So change the ending to bromide. Mercury 1 bromide. If you want to do the method that I taught you here in a second, you can do that. Split it in half. Negative side, positive side. Oops. Positive side. Alright, so bromine has a negative 1 charge according to the periodic table. 2 times negative 1 is negative 2. That means this side must be positive 2. 2 times what gives you positive 2? Yes. Mercury 1. How about this one? First of all, the easy way is to recognize that there is no 2 there, so it must be mercury 2. Polyatomic ion, looking in the back, there it is, carbonate. Carbonate, that's it. All right, let's do it the hard way. All right, so we've got 1 there, we've got 1 of these, and carbonate is a negative 2, so 1 times negative 2 is negative 2. So that means the positive side must be positive 2. 1 times what is positive 2? Positive 2. So it's mercury 2. Carbonate. One more. Pb is lead, and OH is hydroxide. But the question is, which lead is it? Lead can be either 2 or 4. There's a clue. Let's do it the hard way. Hydroxide is negative 1. Lead, we don't know. We only have 1 of them. Split it in half. 4 times negative 1 is negative 4. The positive side must be positive 4. 1 times what is positive 4? The other name for this would be, well, it would be derived from the Latin name, plumbum. The higher of the 2 charges would be plumbic, and the lower of the 2 charges would be plumbus. Plus 4 is the higher, so another name for this would be plumbic. Bic hydroxide. I guess we have an extra one. Barium, oxide, barium, +2, oxygen is -2, nice and easy. But what if you see something like this? Ba2O2. Wait a second, isn't it barium oxide? Actually, it can't be. Oxygen is O-2. In order for this to work, it should be BaO2. BaO2. Sorry. In order for this to work, this cannot be oxygen. One barium with a +2 charge would give it a +2. If this is plain old oxygen, then you would have two -2s, -4. That doesn't balance out. That's because you cannot forget that there is a polyatomic ion called peroxide. Peroxide is two oxygens tied together with an overall -2 charge. It's kind of like mercury was, where mercury had two +1s. This is two -1 oxygens. It's a rare, rare, rare form of oxygen. Two -1 oxygens that are tied together so that it's O2, and they have together a total of a -2 charge. So whenever you encounter something like BaO2 that simply does not make any sense, you need to remember that there is such thing as peroxide. So this is actually called barium peroxide. I think our fun is over. Yes, it is.